For lesson 5, we're going to do a few more different angle types in a circle. So the first one says in circle O, the measure of arc BC is 116 degrees. We want to find arc AB, arc AC, and the measure of angle ABC. All right. So if we look here, AC forms our diameter, so we know we have a semicircle. So we know we got 180 degrees. And then here that makes another 180 down below, so 180 minus the 116 is going to give us 64 degrees. So we found our two arcs now. AC is 180, AB is 64. And now if we want to find the measure of angle ABC, well, it's an inscribed angle. It's inscribed to that semicircle, so we're going to take the 180, cut it in half, and we get a 90-degree angle. So what we want to do here is we want to look a little bit more at these triangles where one of the sides is the diameter. Okay, basically, and one of our angles ends up inscribed to a semicircle. So in the opening exercise, we notice the triangle ABC is inscribed in the circle with one side being the circle's diameter. We also notice the triangle ABC is a right triangle. Do you think any triangle inscribed to a semicircle will result in being a right triangle? And the answer is yes, okay? Because all angles inscribed to a semicircle will measure 90 degrees. All right, so all our semicircles are 180. So therefore, when we cut them in half, because they're inscribed, we're always going to end up with our 90-degree right angles, therefore giving us a right triangle. So in exercise 1, in circle S, diameter PN is drawn. If the measure of arc MN is 110, and the measure and PS is going to be 10, so that's going to be our radius, find the length of MN to the nearest hundredth. Okay, now we know this is a right triangle because we have our diameter, so we're inscribed to a semicircle. We know this radius is also 10, making our whole diameter 20. Now, usually in a lot of these problems, you end up doing Pythagorean theorem. But to do Pythagorean theorem, we would need side MP. So why did they give us this arc MN to be 110 degrees? Well, the reason they did that is that we could take that and find out that angle P is 55 degrees because it's inscribed, so it's half of that 110. And now what do we have? We have a right triangle where we have one side looking for another one and have one of our angles. So therefore, we're going to do trig. So from the 55, I'm going to label my opposite, my adjacent, and my hypotenuse. So we're going to do SOHCAHTOA. Well, what are our useful sides here? Well, I'm looking for the opposite, and I have the hypotenuse. So therefore, I need to do sine. So sine of 55 over 1 is equal to opposite over hypotenuse, so x over 20. We're going to cross multiply. We get x times 1 is x equals 20 sine 55. All right, we're going to go to our calculator. Make sure your calculator is in degree mode. So we're going to do 20 sine of 55. And to the nearest, what does it say, hundredth? To the nearest hundredth, this is going to be 16.38. So we're going to be 16.38 inches for side MN. Okay, so you can see how we took our circle problem and we worked in our trig based on what they had given us. And like I said, Pythagorean theorem is also an option to a lot of problems that look like that. So in circle A, diameter BC is drawn. Explain why angle BEC, BFC, and BDC must all be congruent. And if you look, all three of those angles have the endpoints of B and C. So the endpoints form the diameter. So they are all inscribed to a semicircle. All right. So all of those are inscribed to the semicircle. Therefore, they all have to have the same measure. And what is that measure? It's going to be 90, right? 90 degrees. says explain. So semicircles are 180, and then 180 divided by 2 gives us our 90. So then it tells us the radius of circle A has a length of 5, and it tells us BD has a length of 6. So they want us to find the length of DC. So what can we do here? If we know one radius is 5, we know the other one's 5, for a total diameter of 10. And now if I just redraw this picture real quick here, we have a 6, we have an X, we have 10. We don't have any angles or arcs, so what we're going to do is we're going to do Pythagorean theorem. So x squared plus 6 squared equals 10 squared. 6 squared is 36, 10 squared is 100. We'll subtract the 36 on both sides. X squared equals 64, square root, and you get that x is 8. All right, so that's a way you can take Pythagorean theorem and apply it to some of these right triangle problems. In circle O, shown, diameter AC has been drawn. If OC is 9 and AB is 6, find the measure of arc BC. So just from those side lengths, we can't really find our arc. So what we need to do first is we have to find the only angle that has something to do with that arc, and that would be A. So since angle A is inscribed to that arc, if we can find out that measure, we can double it to get out to our arc. Just like we've been doing, they gave us one radius, so we know the other is also 9, so a total of 18. And now this is going to be another trig problem. Since we know angle B is a right angle, from angle A, what do we have? Well, we have our opposite, adjacent, and hypotenuse. So if we use SOHCAHTOA, adjacent and hypotenuse gives us cosine. So cosine theta equals adjacent over hypotenuse, so 6 over 18. When you're searching for a missing angle, you will arc cosine both sides. So I'm going to go to our calculator and we do second cosine 6 divided by 18. We get 70.52877. So again, we need to keep at least 4 decimal places. So theta is going to be 70.528, and we'll round that up to an 8 in that 4th spot. So now really, if that's the angle, how do we get out to our arc? We got to multiply that by 2. So answer times 2 gives us 141.05. I'm pretty sure this wants to be to the nearest degree. So when we do that to the nearest degree, we get 141 degrees. Okay, so it's using one of our trig applications to find a missing angle, which we then use to find one of our arcs. So we're going to get away from our triangles here for a little while, and we're going to talk about what's called a cyclic quadrilateral, which basically is a quadrilateral where all of the angles are inscribed. So you can see we have a 117, a 74, a 63, and a 106. So take a second and look at that and see what you notice about the angles and or the arcs in this circle. All right, and I want you to focus a lot more on the angles here because that's really the most important piece. All right, and what you should notice is our opposite angles are supplementary. Okay, so when you have a cyclic quadrilateral, again, where all the angles are on the circle, they're all inscribed, your opposite angles are always going to add to 180 degrees. All right, you'll see you get that same effect out of that 117 and the 63. So if we look here, quadrilateral QRST is inscribed to circle W. The measure of angle QRS is 12 degrees less than 3 times the measure of angle QTS. All right, and then it tells you that RQT and RST are equal. So let's deal with those first. So because these two are equal, all right, RQT and RST, they're opposite. So we know they have to add to 180 degrees. Well, if they have to add to 180 and they're the same thing, then obviously both of those have to be 90, okay? Now there is a little bit of a flaw in this picture, okay? So for this to actually be true, we should have a diameter drawn, but that's okay. So if you drew T to R, you would see that you had a perfect diameter would go through W, but it doesn't affect the problem that it's not drawn in there. So now if we look at the other piece here, QRS is 12 less than 3 times the measure of angle QTS. We don't know what QTS is, so we'll call it X. And then 12 less than 3 times that is 3x minus 12. So again, those two angles are also opposite, so we will take them and we will add them up to 180 degrees. So we get 4x minus 12 equals 180. We'll add the 12 to both sides. 4x equals 192. We'll divide both sides by 4. And I believe we should get 48 here. Yeah, so 192 divided by 4 gives us 48. All right. So obviously that gives us angle T at 48 degrees. And then you can either subtract 48 from 180 or plug in here. But what does that give us? We end up with a 132 degree angle. Okay, and again, you could just check that by adding those two up to show that they actually give you 180 degrees. And that's going to be some of our new triangle stuff and then our cyclic quadrilaterals for our circle problems.